Okay, this is a quick overview of servers and clients and how they work. I get asked this question quite a bit. This is just a general overview with, I know this looks like Java code, but it's actually pseudocode. Just to have an idea of exactly what the server does and how the server internally, what the workflow is, as well as obviously the client, what the client does, how that workflow is. I did forget something here. I'll do that now. But anyway, the basic idea is that this bubble here is the server, and this bubble here is the client. This can be a device, a phone, or a browser, or anything that can create connections. Most of the time, the client device or phone or browser is behind a NATed router. So yeah, a connection can only be established from here to here. So it's a one-way thing, okay. The server cannot initiate a new connection towards the client because the client is behind a NATed gateway, so you don't actually have the client's IP. The IP that the server usually gets is a public IP of the router. So there's usually some form of a router here, some router, and obviously here's a NAT. And NAT stands for Network Address Translation, which means that the IP gets translated. So here, the device, phone, browser might have a private IP in the private network. That's either your home network or the office network, or maybe a cell phone network. But then there's a breakout into the internet, and there the local IP gets changed, the private IP gets changed to a public IP, which is this router's IP on the internet. So because of that reason, the server usually cannot connect to the clients. The client can only connect to the server. But this is just who establishes the connection. It's got nothing to do with the data flows that flows inside that connection. So yes, the client can connect to the server, so the client initiates. The client basically goes to the server, hey, I want to talk to you. But once the server says, yes, you can talk, then they both can talk. The server can talk, the client can talk. They can talk whenever they want. There's no, you don't take turns talking. That's basically the concept of a stream. There's a data stream. After a socket is created, once there is a connection established, we refer to it as a socket. If the client connects to the server, there's a socket that opens here. The client can then connect to the server again if it wants to, and then there's two sockets. But at the end of the day, a socket is a connection. So as soon as a socket is opened, the socket is available, you can get the input stream and the output stream, and then technically each socket consists of two streams. A stream that goes from here to here, and another stream that goes from there to there. So if you want to see it, if you want to draw it out, let's say a connection is established, and we call this a socket. Then there would be a stream going that way and a stream going that way. If you close the socket, both these streams will also be closed. But at the end of the day, whenever the server wants to send something, obviously it sends it on that stream. If the client wants to send something, it sends it on that stream. Initially, if you just think of, there's obviously different network layers. So there's your transport layer, your link layer, your application layer, your protocol layer, all those layers. I'm not going all the way to the top. So if you talk about HTTP and stuff like that, yes, then there is an order. The client speaks first, and the server replies. This is not HTTP 1. HTTP 2, they've changed it. Now anybody can speak whenever they want. But this is a level lower than something like HTTP. And in that level, anybody can speak whenever they want. The protocol is the next layer. That is like HTTP. That is the protocol, the communication protocol, or I think it's called the application layer. then you decide who speaks when. But that's not what this is about. This is about simply the socket and the streams inside it and how it works. Now there's usually, as soon as a client wants to connect, on the server side, there's usually a class called a listener. And this listener has a dedicated thread that runs on that listener. So obviously a thread can be compared to a person. So if you have 5 threads, it's almost like you have 5 people doing different tasks. It is a person that just does something. So if you have 2 threads, it means you can do 2 things at once. But a listener usually has a dedicated thread assigned to it. And inside it is usually a while loop. A lot of people just hard code the condition to true. Because this, as long as the server is running, this thing must be running. Only if the server gets killed, you usually stop listening for connections. In Java, for instance, if you want to create if you want to start listening for connections, you create what they call a server socket. The socket is not actually a connection yet. It's just basically the possibility of a connection. If you create a socket, you need to specify what port it needs to listen on. For HTTP, it will be port 80. For HTTPS, it will be port 443. So, but obviously HTTPS will be, it won't be a server socket, it will be a SSL server socket. But it's still a normal socket. You just do a couple of things before you actually carry on. But the first statement is usually the accept command. A lot of languages use the accept statement. That is basically saying, wait until a client connects. So the server socket, which is the server there, you say accept, then it will halt this thread. If the thread gets here, so this is like a person. He's running and he's going to, just thinking of an example now. Let's say let's say this is a receptionist, okay? She's sitting there, she's waiting for the phone to ring. Okay, so she can't do anything else. She only waits for the phone to ring. Most receptionists pretty much do that. Is they sit there and they wait for the phone to ring. They don't do anything else, they halt it there. If a server gets, or if a connection comes in, it is basically like the receptionist picking up the phone. She accepts the call. In this case, it accepts the connection. What then happens, it actually returns a socket, which is then this thing. Okay. But what the receptionist does next is she usually transfers the call to someone else. Because it's another person, it's another thread. So what happens is, in this case, we'll just construct a new person. It won't be an existing person. We just construct a new, we could just call it a class client, which basically is just a reference to the client. It's not actually, it still runs on the server. It's just a class we basically, and a thread we dedicate to the specific client that just connected. And what happens then is obviously we spawn a new thread. Now in here there's also a while loop. But now obviously, because this is a new thread or a new person, this person can carry on with the previous task. So the receptionist, after she redirected the call, she puts the phone down, she waits for the next call. So this one still carries on and accepts new connections. So this thread here is very basic. It just sits and it waits. As soon as the connection comes in, spawns a new class, spawns a new client, gives it the socket. You see I pass the socket through to the constructor of this class. And then you listen for the next one. So it just does those 2 lines basically. Very straightforward. So this is called the listener. And it's usually a very, very simple, straightforward task, or class, or thread. The client, on the other hand, can get a lot more complicated, because that's where you actually start using these streams. How it works is you've got a dedicated thread here, and this is very important. The dedicated thread is only used for reading, not for writing. So that is waiting for data to come in. So if there's a dedicated thread here, that thread basically only uses this stream here, the one that goes that way. This side, you can also have a dedicated thread while true, or let's say while connected. And this one also has a socket.read. Okay, but this thread will use that stream. On both sides, obviously, on this side, the input and output stream will be reversed on this side. I don't know if that makes sense. So on this side, let's call this stream A and stream B. On this side, stream A will be an output stream, but on this side, stream A will be an input stream. On this side, stream B will be an input stream, and on this side, stream B will be an output stream. But when you have a thread that reads, it always operates on the input stream. On this side, the input stream is stream B. On this side, the input stream is stream A. So basically what happens now is as soon as you say, cool, read data from the stream, the same thing happens. The thread gets paused there and waits until data arrives. So basically this thread almost sleeps. It's the same as the except statement here. A thread just sits there and sleeps and waits for data. Obviously two things can happen. Either data can arrive or the connection can be cut. You need to code for a break-in connection because networks aren't reliable, especially when it comes to cell phone networks. You can receive a network cut at any point. You can be busy reading data or busy writing data, and as you write it, it just cuts. That's obviously if the device or something loses signal. So yeah, that's something you definitely have to code for. That's also why you have stuff like acknowledgements and stuff like that. If the client sends something, the server needs to send something back to say, I have acknowledged this. So that the client knows when the connection is cut and re-established, he doesn't have to send it again. So that's quite a lot of mechanisms you're going to have to write to make sure that whatever data you send here does actually arrive here. If you didn't get acknowledgement and the connection is cut, you need to connect again and send the data again until you get an acknowledgement. Okay. You can set up a socket to, if you read, that it doesn't wait. It just checks if there's data, and if there's no data, it still carries on, so it can still do other stuff. Because sometimes what can happen is, obviously as you can see here, we create a new client for every connection that comes in. Now obviously there's lots of these clients, okay? They all have sockets coming into the server. So for each socket you're going to have a new class created and a new thread. But if you have, like we have, we've got a couple of thousand devices in the field. I mean, we're sitting at 24,000 now. Basically, that means if they're all running on the same server, you're going to have 24,000 instances of this class and 24,000 threads. Then you get a thing that you call thread overhead. Your thread overhead becomes so big that your CPU spends 30% of its time switching between threads. So you waste a lot of CPU power. So what you can then do, instead of having a while loop here, you can just let the CPU go through all the classes and just check if there is data on the sockets and then processes it. So that's called a non-blocking socket. So you get a blocking socket and a non-blocking. So blocking versus non-blocking. Non-blocking is if you read, it doesn't wait. It either returns null or it returns data. That's it. A blocking socket will sit there and wait. Some of them you can actually also specify a time that it needs to wait. So then it's almost like a hybrid between blocking and non-blocking. You can say read, but only wait 10 seconds. If there's no data, then return null and carry on. then you can have a sort of hybrid solution. Okay. And if you, obviously, like I said, the threads operates on the input streams. That's mainly because the output streams is some other mechanism that uses the output stream. It either maybe a user, let's say it's a chatting application where you can chat to people like WhatsApp or Skype or whatever. Then what will happen is obviously Skype will listen on the client side. It will constantly wait for data to come in, which is an incoming message for someone else. But as soon as you type a message, you send it. Whatever thread manages the GUI, that thread will then go grab the output stream, send the message, and then go back to whatever it's doing. And that could be different threads. It could be a thread that runs on a timer that does something else, or it could be a thread that comes from the GUI or whatever. There's usually not a dedicated thread for sending. You do need to obviously look at synchronization so that two threads don't send at the same time. But most sockets and input streams has that already built in. If two threads try and send data at the same time, it will actually halt the one thread, wait for the other thread to finish sending, then it will basically release the first thread and that one can send. Okay. So that's the basic concept. Obviously what you can also do is as you construct new clients here, you can push it into some sort of a hash map mechanism. Because if you want to send data to a specific client that's connected, you need to be able to find that client and send to it. Then you can maybe, if you have a hash map where the key is maybe the client ID, then you can just find the client ID in the hash map and then grab the client and then get the output stream and send it. Because obviously there's going to be a lot of these, just to draw it out. There's a lot of these and they all have sockets, obviously connecting to the server. And each one of them obviously will have their own dedicated instance of this class with a dedicated thread. I think that covers pretty much everything.
Quick question, that if the connection is cut and has been re-established within a certain time, does it use the same thread again or does it create a new thread?
No. Most of the times it completely destroys the thread, it completely destroys the class. And a new one will get created. So it does get a little bit complicated because now your logic in the server and you need to obviously think of that. So usually what happens is it can go a little bit further. It can complicate quite a bit where your client becomes a lot more simple, where you don't really write your logic in the client. You create like an extra class and you write your logic there and it basically pushes it into an internal queue. So you can have obviously like a memory somewhere with, let's say, the client ID. Let's say the client ID is 5 and then maybe some data that needs to be sent to client ID 5. But this never gets destroyed.
Okay.
So when a client connects, it finds its record. So it sees, okay, cool, I'm client number 5. Finds its records, and whatever data is there, it will send. You see, so then it gets very simple. If the connection gets cut, this thing gets destroyed, a new one gets created, it will then know, well, it knows it's client ID 5 because obviously the client will say on the stream, I am client number 5. Or it will either send login details or whatever. And then this thing can then figure out, okay, cool, I'm number 5, it'll find its stuff again and send it again. So that's another way to do it. And obviously if the client then sends back an acknowledgement, you can even have IDs here. You can say, cool, this is request number 1, 2, 3, 4, 5, 6. So let's say the client sends request number 1. It will send request number 1. The actual device will then reply and acknowledge and say, yes, I have received request number 1. As soon as it gets that, then it will delete this one from memory. Maybe then the connection gets cut, and the device then senses that the connection is cut. It will re-establish a connection. It'll go, yeah, new client gets created. The device says, cool, I am client number 5. It'll go back. It'll see, oh, that one sent. Let's send number 2. then it will send number 2, this one will acknowledge number 2, it can delete number 2. You see, so that's a way to handle connections that are cut unexpectedly. There is a couple of other, this is your basic model of how to do server clients. There is a lot of other models. Like for instance, what we use in our system is that we actually use the same thread here to start this thread to basically have a quicker response time. But then you have to have thread pools set up and you have to reuse threads. And then you don't have a while loop here, you basically start this class over and over. But you have threads waiting here while another thread accepts. So as soon as one thread accepts and starts doing stuff, the next thread already accepts. And we do the same thing here, so that you can process stuff simultaneously. It does, when you look at the code, it can be confusing because there's no while loop here or here. You basically just start this class over and over, and you start this one over and over. So you always make sure that when you read or when you accept, there's another thread waiting right there, another thread waiting right there. So as soon as you read and you process the data, while you're processing the data, there's already another thread reading the next data coming in. You see, then you can optimize your data flow quite a bit. Especially if your processing of the data can take long. Let's say this thing takes 2 or 3 seconds. It could be a problem because in those 2 or 3 seconds, more data arrives from the client. Especially if there's a lot of requests coming in and there's high data flows on one socket. This is obviously only if it's on one socket. If it's on multiple sockets, it's not a problem because then each of these will be a separate thread anyway. Okay. Is there any other questions? Okay, and also this is obviously TCP connections. Okay, so the socket is technically a TCP socket, TCP IP. The model for this is because a connection is established, agreed upon, and data is flowing. It's got error checking and or what do you mean, CRC checking, as well as making sure that the data arrives in order, etc., etc. That's basically what TCP/IP does. If you go to UDP, then the model changes slightly because your packets doesn't arrive here; they technically still arrive here. So the model changes slightly. But I mean, TCP is the most commonly used socket out there. We don't really use UDP that much, except when it comes to very like video streaming and gaming. That's sort of the only place we really use UDP. Other than that, we always use TCP/IP. Because we use TCP/IP for the socket, whatever language you're coding in here doesn't have to be the same as the language you're running here. Okay, this could be written in C++. This could be written in Java. It'll still work. This could be PHP, Apache, and this could be Java, and it'll still work. As long as the protocol, whatever data flows through the socket, is a standard, and they both speak the same language inside the socket. So, if you write your first chat application, you're going to have to invent your own language that runs through the socket. So you're going to have to say, if let's say the client says, I am client number 5, you're going to have to invent a protocol of how to say to the server, I'm client number 5. So you're going to have to, they usually use operations or command types. So you'll first say what you want to say and then you say it. So you'll say, cool, you'll send let's say a number, like the number 10. You'll send the number 10 through. And on this side, it will read number 10, and then it knows, cool, oh, number 10 means he wants to tell me who he is. And then the next data is who he is. You see, but that number 10 needs to be agreed upon on both sides. If this side sends the number 10 first, then following number 10 is who he is. And then let's say there's another number, number 20. If this one sends number 20, it means, oh, he wants to send a message to another client. Then you need to say, cool, okay, after the number 20, he needs to send me where he wants to send this message as well as the text. You see. So that's basically the language almost. That's a whole other training session on its own, how to define that language. It can get quite complicated.
Is this where we use the adapters, for example?
Yes, yeah. So, but yeah, that language is usually referred to as the protocol as well. It's the communication protocol. Technically, this is also protocol. TCP/IP is also protocol, but it's a protocol on a different network layer. Okay. The protocol that flows inside the socket is called the application protocol. If you want to go Google it in the network layers. Okay. So TCP/IP just basically makes sure that whatever data is sent here is received here. And it makes sure that the order in which you send the data here gets arrived in the same order you send it here, as well as it does error checking, because obviously with networks, if a network cable somewhere doesn't work properly or there's lots of interference, it'll make sure that the data doesn't get corrupted from here to here. That's what TCP/IP does. So other than that, TCP/IP doesn't do a lot. The IP part obviously makes sure that it gets from here to here and not from here to somewhere else. But the TCP part makes sure that it gets from here to here in one piece, in the same order, so you don't have to do error checking. So a lot of protocols still has CRC checking, but that's actually not needed. If you're using a TCP connection, you don't need to do CRC checking. The cool thing about if you do CRC checking, you can actually switch to another protocol like UDP and your application will still work. Because UDP doesn't do CRC checking. It also doesn't do the ordering of the packets. So UDP is a lot, it doesn't give you as much functionality, but it's a lot faster than TCP/IP. So that's where UDP has an advantage because it does less, it's quicker. And it's a protocol that sort of, if you get data and it's corrupt, you sort of just discard it and you wait for the next data. That's why it works with like video streaming. If you miss one packet, you just don't update a couple of pixels on the video, but the next frame is coming anyway, so you just ignore it and you carry on, you wait for the next frame. Or when it's a video game, if you lose one or two packets, it's not the end of the world. Maybe the character will just jump around a bit, but then it will go again, because the updated position is coming again. So you don't even need to tell the other side, listen, I haven't received this data, send it again. You don't need to do that. You just wait for the updated information anyway. So UDP is good if you're sending a lot of updates all the time. Update, do this of the same thing. So let's say like a car moving in the world or a character moving in the game, its position, it constantly updates. It's the same character, you're sending the information again and again and again, but it's small changes. Then UDP is actually very nice for that because it's quick. Okay, does that make sense? Any questions? Nothing. Yeah, I think that's pretty much it. Oh, in Java, to get the input-output streams, you just say socket.getInputStream and socket.getOutputStream. Then return those streams. Okay. And yeah, then you can obviously, so you don't actually say socket.read. You actually say, you first get the socket's input stream and then you say the input stream.read. Okay. Cool. Awesome.